This FedGov Today program is sponsored by Maximus. On this edition of FedGov Today with Francis Rose, the Naval Research Lab sets its sights on robots in space.
Human time in space is very precious, and we think that we can do these capabilities with robots and really advance the final frontier.
Dr. Samantha Chapin of NRL on FedGov Today in just a moment. Uniting program strategy, advanced technology, process, and execution for a more efficient government, that's Maximus. Every program, every service, every time, that's innovation forward. Learn more at maximus.com/federal. A Naval Research Laboratory breakthroughs using a flavor of machine learning to adapt robotic systems in space faster than ever. Dr. Samantha Chapin is space roboticist. Dr. Kenneth Stewart is computer research scientist at the Naval Research Laboratory. Folks, welcome. Thanks for joining me today. Ken, I want to start with you. Define reinforcement learning and just tell me about the flavor of machine learning that it is, according to what I read at least. Welcome, Ken.
Hi, welcome, and thanks for having us. So reinforcement learning in a nutshell is basically where, like, say, a robot or an agent tries to learn using rewards and getting those rewards by interacting with its environment, which is, if anyone has pets or knows anything about dog training, is a lot like that, where, like, if you want a dog to, like, do a command, like you tell it to sit and the dog sits, or you tell it lay down. Like, you usually train a dog by giving it food rewards, right? Like, they do their thing that you want it to do, then you give a treat, and then they know, oh, like, I got a treat for doing this. This is what I'm supposed to do, and I'll do it next time. Well, it's kind of like that, but you do that with robots, where it's like, if the robot does the thing you want it to do, like you're telling it to do, like, like, hey, robot, move over there. Then once it actually figures out how to move over there, you give it a treat or a reward, and then it knows to do that next time.
Sam Chapin, welcome. How does this type of machine learning differ from other types, and why did you and your team decide that this was the way that you wanted to pursue the particular challenge that you undertook here?
Yeah, so we're doing a lot of research into robotics for space applications. So in space, you're restricted in a couple ways. So it's expensive to get to space, and when you're testing in space, there's a high, they don't really have the tolerance to risk is really high, or a low risk tolerance. Like, they do not want to take risks. So right now, when they're doing robotic operations, they try to take the safest thing. And so that can lead to a lot of robotic operations be something kind of like joysticking. So, kind of like you can control a little robotic car, they're doing that on the scale of, sending very specific commands. And what we want to look at is, how can we make that more autonomous? So how can we make it so that the robot is observing its environment and making decisions for itself? And so the reason we decided to implement reinforcement learning for this task, for the free flyer, the Astrobee on board the International Space Station, is that we essentially determined that reinforcement learning allows you to have the robot train in simulation over many, many environments, and you can slightly change things about those environments. So you can make them, have things be slightly different, slightly wrong. Like the real world, things aren't as we expect. Everything is not always the same. It's not perfect. And so we can simulate those slight variations inside our simulator, and then train a reinforcement learning policy that's able to still perform even if something's not exactly the same. So we can vary things like the mass of the robot. And if that's not exactly what we expect, if we have a payload there we're not expecting, it can still operate and perform the desired function that we're trying to get it to do.
I read that reinforcement learning can enable robots to perform very complex tasks, such as assembling large space telescopes and solar power beaming stations. Is that the reason that the International Space Station was the right place to do this?
So the reason the International Space Station was a great place to test is that they already had the Astrobee robot there. And NASA had it available to different research scientists to be able to test algorithms. So again, it's very expensive to put things in space, but they already had that platform in there, and they were open to having people try complex algorithms that aren't the norm. And so that's really perfect, and why we're able to do our tests, because NASA had this Astrobee platform we could test on. But the International Space Station itself is currently our best example of large assembly in space. It's about the size of a football field. It's so big that you couldn't send that up in one launch vehicle. And if we want to continue to have bigger structures in space, be able to have a higher capability, we're developing the robotic technologies that you're going to need to assemble something on the scale of the International Space Station or bigger, or to service things like Hubble Space Telescope, but do it with robots. So that's kind of our larger mission, that this test is kind of our first step forward into putting that really complex reinforcement learning algorithm on a real robot in space and having it work in the 5 minutes that we had to test and having it work the first time. So we're really happy we've made that step.
Ken, how did you set up the experiment, and what was the way that you determined you were going to at least be able to test for the results that you hoped to achieve?
So we set up the experiment. Well, we basically decided to do like a walk, crawl, run approach, or like we'd, test out something that we knew was very feasible first and then build complexity from there. Unfortunately, we only got to the walk part, which was basically, get the Astrobee to be able to move in space, given a command, like, if you give a command, like move to this particular position orientation, go there. And we figured this would be a good start because we could set up the experiments using this NVIDIA Omniverse simulator that we've been using a lot of development in, where we could, very rapidly like test out, this on and train like, tens of thousands of robots in parallel in order to like within hours get like a testable policy. And then what's really nice is that all of the Astrobee code is open source, so we could get a simulator that NASA uses to test and verify their policies before moving it into hardware. So we then took our policy, we trained in our simulator, tested it on their simulation environment, verified that worked, and then we did hardware testing from there, where we tested on the Granite table and verified that worked. At first we had some problems, and then debug, reiterated, got it working on the Granite table. Then that gave us confidence to then test in space on the International Space Station.
And what are the applications potentially for using this technology outside of the experiment that you did? What did you learn from the experiment that you think will apply in other areas?
So I think a large area that we're interested in is this thing called ISAM, which is in-space servicing, assembly, and manufacturing. So kind of this larger suite of capabilities to be able to operate in space and do things robotically and autonomously. So you're not having a human on the ground kind of, babysitting a robot, making sure it's doing all the tasks you want. So something like what we did for the Astrobee, where we were just having it learn how to move from one position to another, you could use for basic controls for things like inspection. So you could have a robot like Astrobee be able to fly around something with a camera and be able to just take imagery and kind of assess what the state of a structure is, either inside of a space station or outside of a space station or on a satellite. But we want to, in future research, go even farther and try things with more complex operations. So things like robotic arms, manipulating objects, assembling structures, and then using those to also service things. So that's kind of the hardest test case scenario, is like if something is broken, you're not exactly sure how it's broken. Can we have the autonomous ability to assess the state of whatever is broken, if it's a satellite, if a solar array is not deployed, if some flexible sheeting is covering something that's supposed to deploy and it's not deployed? Can we have a robot be able to go in there, assess it, and then actually rectify whatever that error is? Because, a lot of spacecraft are in, remote orbits. We don't, human time in space is very precious. And, we think that we can do these capabilities with robots and really advance the final frontier.
Are there other opportunities to platform these besides the International Space Station, or is that really because of the fact that it's already there and the tools that you need are already there? Is that really the ideal platform for you to do this testing?
So historically, the International Space Station has housed so much research from so many companies, so many countries. And so I think because it's that unique international place where you can test science and get results in a zero gravity environment that you can't get on Earth, right? We simulate it in our simulators, and we can do a facsimile of it on the ground with our Granite tables, where we basically have 3 degrees of freedom instead of 6 degrees of freedom. And it's kind of like an air hockey table. You can float things, so you can get kind of a good idea of how it's going to perform, but you're not going to know if something works in zero gravity unless if you're in zero gravity. So right now the International Space Station is such a great place to be able to do testing. We're hoping, in the future, whatever, space ecosystem exists, if there are other platforms, we're kind of agnostic. We're very much, how can we push space robotics and, with whatever is available at the time to kind of show that these autonomous systems can operate in real time when they need to, without any human interaction.
Either on a personal level or a professional level, what would you like to test next? What's the next kind of evolution in what you're doing in this area?
When we tested the Astrobee, that's a free flyer inside of the International Space Station. So we have the zero gravity element, but it is inside of a pressurized air capsule. So humans are living in there. So that is not exactly the same as if we were testing in a zero gravity environment in a vacuum, like fully in space. And so I think at least for the type of stuff we were doing on Astrobee, if we could test it on something like a CubeSat, that would be super cool to be able to just say, it's fully in space and vacuum, it's still operating. We could control a CubeSat in, using these novel reinforcement learning algorithms when traditionally they've been, using very, the same kind of systems for decades. So I think our goal is, be able to increase the level of complex autonomous operations we're doing on the ground in our testing environment, but also incrementally try to get those opportunities in space to really test things out and show people, hey, you shouldn't be afraid of this autonomy. It's going to be able to make it easier to do operations you want to do, and we can make it really robust and able to handle a bunch of different types of failures.
Sam, Ken, it's great to talk to both of you. Thanks very much for coming on to discuss your work with me. I appreciate it.
Thank you so much.
You can learn more about NRL's research on robotics in space on today's show page at fedgovtoday.com. Threats to the energy grid are intensifying, according to the director of the Office of Cybersecurity, Energy Security, and Emergency Response at the Department of Energy, Alex Fitzsimmons. He'll tell you how they're intensifying and his office's role in helping on the next FedGov Today TV. You can watch the debut on ABC7 in Washington and on the FedGov Today YouTube channel at 10:30 Sunday morning. If you miss the debut, you can watch anytime at fedgovtoday.com and on YouTube. The next FedGov Today podcast is coming Thursday. The Interior Department's Zero Trust Journey is in focus. Lou Eichenbaum recently stepped down as the CISO at Interior. He'll tell you about that Zero Trust Journey. To make sure you don't miss it, follow the show on Apple Podcasts, Spotify, or wherever you get your shows. And you can listen on demand at fedgovtoday.com. I'm Francis Rose. I'll talk to you then. Thanks for listening.